Okay, great. Okay, great. Thanks everyone for attending the meeting. My name is Evangelos Farantatos. I'm with EPRI's Transmission Operations and Planning Group, and I'm leading the work related to application of synchronized measurement technology in transmission operations and Uh, basically, that includes PMU applications and wide area monitoring systems and wide area monitoring protection and control. So, in this presentation, I would like to present the results from a study we recently did in collaboration with Entergy. You see the topic localizing cyclic industrial load-induced forced oscillations at the energy grid using synchrophasor measurements. Apologies to those who attended the recent NASPE meeting a few weeks back. You might have seen, you saw a similar presentation from my colleague Lynn. Um, uh, we would like to present this to this IEEE task force as well. And before going into the details, I want to acknowledge the collaboration and the support from Entergy. It was a great collaboration with different teams within Entergy, including the planning team, generation team, and also the PMU team. So let me start with background and motivation. Basically, what happened is that Entergy has been observing consistently oscillations, small magnitude oscillations with a wide frequency range between 3 to 7 hertz in different regions across the Entergy grid territory. And they have been observing these measurements for a while now using the PMU measurements. Initially, when they first observed them, it was not a big concern. But what created the recent challenge and initiated the project was the fact that in a specific region and for a specific generator that they have in a specific region, they are doing some retrofits or changes in the turbine and generator system, and they were concerned about potential risk of resonance between those oscillations with the torsional mode of that turbine generator system that they were doing upgrades. So there were concerns about potential damages in the plant and things like that. So the objective of the study was basically to use recorded PMU data and try to identify what is causing these oscillations and what is the source, and basically suggest potential mitigation measures and detailed studies that would need to be done to basically um, um, try to identify what is the most practical and cost efficient way to mitigate that risk. So that's the motivation. And as a kind of a spoiler alert, you saw from the title also that after the analysis, we basically found and validated that the source of those oscillations were synchronous motors driving reciprocating compressors. So basically, these were the oscillations were caused by industrial load plants within specific areas that they are using those synchronous motors with reciprocating compressors, and because of their cyclic loading scheme pattern, they were introducing, or they are introducing in the system those forced oscillations. So we'll discuss more details in the next slides. So what was the process? So first of all, we worked with Entergy, but also we had support from Grid Protection Alliance, GPA. Most of you might know Richie Carroll. So he helped us with basically getting access to Entergy's Open Historian PMU database. So that was very helpful because basically Entergy didn't have to, uh, create Excel files and large Excel files with data and send them over to us, and we didn't have to go through that process again and again. So we got access to the Open Historian database, and whenever we needed data for a specific time period, we were able to access that and use the data. In terms of the tools and methods that we used, we started with a simple FFT analysis on the data on different data sets to basically confirm the existence of the modes and do some calculations regarding the magnitude and the energy of those modes. But we also used the EPRI's forced oscillation localization tool. I believe there has been presentations in this task force from my colleague Lin Zhu with more details about this tool. So we use them as well. So we followed kind of a step-by-step process to try to identify what was the source of those oscillations. And through the slides, I will walk you through that process. But as you see here, basically we started with suspecting usual suspect. We started with usual suspects with generators. We found out that this was not the reason. Then we were starting suspecting loads. We identified these were the loads, and then I will explain the process or how we got to identify which specific substations and actually which specific feeders and motors were the ones that were causing those are causing these oscillations. As I said, we used the one of the tools we used was the EPRI's forced oscillation localization tool, FOLT. This has been developed in collaboration with University of Tennessee. And basically, the version we used, because this is ongoing work that we keep on adding features year by year, but the version that we used was a version that can process PMU data. And so basically, we can analyze oscillations with frequency from low values, less than 0.1 hertz up to 15 hertz or so. You've seen presentations in this task force also that for higher frequency oscillations, PMUs have limitations. So that's why we say up to 15 hertz. That's a reasonable kind of frequency rate that PMU data can be useful. The tool has different methods for location. The most accurate, based on our experience so far, is the dissipating potential method. This is very similar to the well-known dissipating energy flow method, so it's a small variation. But the tool has also other methods, including the oscillation magnitude and oscillation mode angle method. Again, we're not going to go into the details here regarding this. That's one of the EPRI tools that we use for this study. So the tool is basically using voltage. We can use a different type of data, so we can use voltage, frequency, and currents. The currents, if we have currents, which we used in this case, they help basically increase the observability of the grid. So, for example, if there is a bus unobservable, let's say on the left-hand side, and if we have a PMU here and we have the voltage and the current flowing through that line, then we can estimate the voltage here. So that's a function implemented in the tool so that increases the observability. And that was helpful also in this study, as I will show in the slides later. So again, when we started the work, we first again started looking into the generators as usual suspects of forced oscillations. So we used different data sets that we got from the Open Historian database, and through FFT analysis, we were trying to see whether these basically these oscillations with again the frequency range between 3 to 6 hertz were observable for different operating conditions. So you see that basically we tested different data sets from different days with different operating conditions, with some generators connected, other generators disconnected. Uh, so again, we did that to try to identify if there is a pattern, if maybe the oscillations go away, if a generator is off, or something like that. So this was kind of the initial thought, but actually the conclusion from this initial analysis was that the generators are not causing the forced oscillation. So the generators, none of the generators are the sources. So basically, yeah, we had to continue the investigation and look at other potential candidates for introducing loads, introducing oscillations. So then we started looking into the loads as suspects. Um, and basically, you see here on the bottom of the slide, kind of a simplified single line diagram of one portion of the system. So basically, in this case, this is where we started using the tool that I mentioned before, the EPRI FOLT tool, and using both voltage and current and frequency measurements. We basically the tool estimated a specific substation as the source for the oscillations. So looking deeper into the kind of topology of the system, so what we have here, we have a plant on the left hand side. So in this plant, there was a PMU, and then that PMU was measuring the voltage and the current on that line that was connected to that substation. And then that substation, is kind of radially connected to other substations. And then on the right hand side, you see there's also another plant. This also has PMU. This house also has a PMU. So the again, based on the analysis, based on the all the data, the PMU data that we used as an input to the tool, we identified the substation A as the candidate source for the oscillations. Now, the one of the data sets that we collected was during an operating condition where basically there was an unplanned outage of the line between substations C and D. So basically, when for that operating condition, we still saw we could still see basically the oscillations in the data sets. So that based on all this information, then the conclusion was that the suspected source locations for these oscillations were those three substations: substation A, substation B, substation C. Again, based on the availability of data, the tool and the method that we used was indicating substation A, but because we don't have PMU data here on the lines between the other substations or within the other substations, then we could, we could not verify whether the oscillations were, only from substation A or other substations were also contributing. But based on the data set here with the unplanned outage that I mentioned before, we were able to narrow down to these three substations. So once we had that, then the next step was basically in collaboration with Entergy. What Entergy did is that they installed temporary sensors at the with PMU capability at the high voltage buses of those three substations. So you see here that the boxes with the orange boxes are basically the additional temporary devices with PMU capability that they were installed in those substations. So they were installed within the substation to look into the feeders and into the loads within the substation, and then also on the line to monitor the current between. So once these were deployed, and the data we could collect from these was again frequency, voltage, and current at 60 hertz reporting rate. So this was very helpful. When these were deployed, then we were able to collect data or record data for some amount of time. We analyze the data and we see that we could still see those oscillations of different frequencies, specifically 4.62, 5, 5.46, and 6 hertz. So all these modes were visible or observable in using those sensors. So that was very helpful to basically narrow down and see exactly, which are the sources of those modes, oscillation modes. So specifically for substation A, we were able to see that we were able to see or observe those oscillations in the measurements from two transformers, transformers 3 and transformers 4, transformer 3 and transformer 4. And in this case, we could see the 4.62 and the 5 hertz oscillations. For substation B, we didn't identify any source. As you can see here, the data were not indicating that any load within that substation was the source. While here you see from substation A, specifically from these two transformers 3 and 4, that we can see the oscillations with this frequency. And then substation C also from two specific from three transformers. Actually, transformer 1 and 2, we could see oscillations at 5.46, and transformer 3, we could see at 6 hertz. So that was again based on analysis of the data at those substations that I was showing before, ABC, at the high voltage side. So then Entergy again, basically they talk to those customers, their customers, the industrial loads in these substations, and specifically for substation A. So for this substation, they got permission, and again in collaboration and support from the industrial load customer, they were able to install or deploy these temporary sensors at the low voltage side. So in this case, we were able to go even deeper into the system to try to identify what equipment is creating those oscillations. So this is basically where we, after we install those sensors at the low voltage buses, this is where we were we confirmed and we validated that the source for those oscillations were the synchronous motors that were connected at those substations. And these are synchronous motors that are driving reciprocating compressors. So again, these are motors that are used for industrial processes, and they have this cyclic load pattern. And the very interesting thing was that basically we saw that as you know, as expected based on the physics, that the frequency of the oscillations is related to the motor speed. So, for example, the motors that they have synchronous speed at 277 RPM. If you do the math, this is what creates the 4.62 hertz oscillations. The motors that that have speed 300 RPM speed, that this is creating the 5 hertz oscillations. So basically, if I go back and show you all the frequency ranges that of the oscillations that we were seeing across the system. So again, in the system where we're seeing oscillations at 4.62, 5, 5.46, and 6 hertz, and that and we were at that point we managed to, and we were successful in basically indicating that the motors are the ones that are creating those oscillations, and the frequency of the oscillations is correlated or is dependent on the RPM, on the nominal speed of those motors. So you see again in substation A, they had motors with 277 and 300 RPM. So this is where the 4.62 and 5 hertz oscillations were coming from. And again, we were able to see those when analyzing the data with simple FFT, the PMU data. And basically, for the other substations, for the substation B, we said there were no motors. In that substation C, they had motors there, and they were introducing the 6 hertz and the 5.46 hertz oscillation. So that's basically the analysis we did. Another interesting data set that we analyzed was during a plant outage of one of the motors in substation C. So you see here the FFT analysis of the line current from the plant A to substation A using during that period where we had the outage of one of the motors. So I want you to focus on the purple line, which is the 5.46 the 5.46 hertz oscillation mode. So you can see that basically. So basically, what you can see here is that there are variations in the magnitude of the oscillation before and after the motor stopped, and also after the motor restarted. So what we suspect was happened during that time period is that, so initially before the motor stop, you see that the energy level of that oscillation mode is at a specific value. Then it increases, and what we suspect is happening here is because, again, this was a planned outage. What the load customer did is that they, in anticipation of one of the motors being stopped, they basically increased the loading of the other motor. So basically to compensate for the production, let's say. So before the motor stopped, you see that the energy increased. So again, here we suspect that the customer, the industrial customer, increased the loading in another motor. Then here was the plant outage or the plant motor stop, and you see a significant decrease here in the energy of that oscillation mode, which again kind of explains, it can be explained from the fact that the motor stopped. So this is another way, kind of validation that motor was creating or is one of the source of those oscillations. So you see here that the energy got reduced, But then here you see a small increase, and what we suspect here is that if you see here the value is below the pre-event, let's say, value. So we suspect here that the load customer increased further the loading of the other motors within the substation to basically bring the, let's say, the production level to the same level as it was before before the plant outage. So you see that here, after that small increase, the level is similar to what we had initially. And then we get to the point where basically the motor was restarted, and you see here the increase as expected with the motor restart. And then probably here at this point, there were still some kind of updates or kind of rescheduling of the loading of the different motors within the substation. And eventually we got back into a steady state. So that was also an interesting data set that we studied that was showing how the energy level, let's say, of that oscillation mode, specifically at that 5.46 hertz, which is associated again with the motors with a specific speed and RPM, how stopping and restarting and adjusting the schedule of other, motors in service, how the energy level of of that oscillation mode was changing. So that was the analysis, and the last kind of task that we had for the project, as I said at the beginning, was to discuss about potential mitigation measures. So we categorized them into three kind of categories. The first one is solutions or mitigation measures that can be done from the load or the customer. So one option here is basically to reduce the magnitude of the pulsation by proper sizing of the motor inertia. Um, that might be not the most practical, but that's more of a planning mitigation measure. Another option is basically to use variable frequency drive VFDs to modify the oscillation frequency. As we saw, the oscillation frequency depends on the RPM of the synchronous motor. So with the use of VFD, that oscillation frequency can change, and it can be basically it can be arranged so there is no risk of resonance with the any torsional mode of generators in that area, which again was the initial concern for this analysis. The other category is the transmission and utility solution. So basically, what the transmission utility Entergy in this case could do. And two options we listed there is to basically install devices to suppress the oscillations, devices such as STATCOM or batteries. Now there's a lot of discussion about e-STATCOMs and GFM batteries, etc. Or basically another option could be to design and deploy a special protection scheme to trip the motor if the oscillation magnitude is significant and exceeds a predefined threshold. And then the other categories from the generator side. So what the generator could do is basically install torsional damping controller to avoid or prevent any damage to the generator turbine system if there is a resonance. Again, this was just a listing of potential mitigation measures. It was not within the scope of the project to do any detailed studies about any of these. Some of these require very detailed studies with EMT models, etc. If someone wants to go to that route, but again, this was just a list of the different options. So that's basically the summary of the project we had and the analysis and the results and the outcome of this investigation. So to summarize, basically, the driver or the motivation again for this analysis was multiple forced oscillation modes that were observed in the Entergy territory, in the Entergy's grid territory, in different areas. So we used PMU data from Entergy's PMUs, but also from additional temporary sensors that were deployed during the project to locate the source. We were successful in identifying that the source of those oscillations were synchronous motors with driving reciprocating compressors. The frequency of those oscillations correlates with the speed, the RPM of the motors. So you see here the correspondence between the RPM and the frequency. Again, the reason for the investigation is to basically um, to investigate whether there is a risk of resonance between those oscillations and the torsional mode of generators in different areas within the energy system. In terms of the analysis, as I said, we used simple conventional FFT to basically observe the oscillations and the modes in the data sets, in the PMU data sets that we used. And we also used EPRI's forced oscillation localization tool to support the analysis and pinpoint to the source. And regarding the potential mitigation measures, again, we categorize them depending on who would be the responsible entity, whether the load customer or the transmission utility or the generator owner, and we list different options that we discussed before. So that's the summary of the project and investigation we did. So maybe with that, we can open the floor for questions or comments.